So as you can see, chapter 3 is our water chapter. And the nice thing about chapter 3, it's short, it's to the point. We get into the properties of water and what makes all life possible on Earth. The nice thing about chapter 3, I only have 40 slides, so this is definitely a treat. All right, so going into those slides. So water is ultra important. Without water, life would not be possible on Earth. And so it is the reason why we talked about in the previous chapter with chapter 2, that water is going to form polar bonds. Water itself is a polar molecule. And so it is going to form hydrogen bonds. I should call them hydrogen bonds with other water molecules. And because of that, that's what makes life possible. Just kicking the dogs out because I know they're going to bark. All right, so water is a biological medium on Earth. It is only common substance to exist in the natural environment in all three physical states. So liquid, solid, and gas. So the structure of the water molecule, like I was telling you, that is what makes it special and able to interact with not only other water molecules, but other polar molecules also. And so there's going to be unique emergent properties that we're going to go over. We're going to go over 4 of water's properties that are going to make Earth suitable for life and because of the water. And so if you recall previous chapter, the water molecule is going to form polar covalent bonds. And that's because the electrons within the water molecules are going to have a greater affinity to hang out closer to the oxygen oxygen atom instead of the hydrogen atom. And because the electrons like to scoot closer to the oxygen atom, that causes an unequal distribution of electrons. And that unequal distribution of electrons is literally what causes one side of the water molecule to be charged and the other side of the water molecule to be opposite charge. So one will be negatively charged where all of the electrons like to hang out more, and where the electrons leave, that's going to cause a positive charge. And I said leave, I should say hang out less. So your polarity, oh, we've already talked about that. So check it out. That's what we're looking at here. We are looking at individual water molecules. Let's go ahead and draw them out. This is one water molecule. And within that one water molecule, you are going to have polar covalent bonds within the molecule. Okay, so here's one water molecule and the bonds, polar bonds, are within them. So between water molecules, you are going to find hydrogen bonds. So the hydrogen bonds are between the water molecules. I actually would like to make that not so dark. Let's see. Instead of highlighter, we'll pin it. Between water molecules are those hydrogen bonds. These hydrogen bonds easily break and reform and break and reform. Okay, so they are considered weak bonds. The polar covalent bonds are strong. So these are the weakest bonds, and the covalent bonds are strongest. If you recall, in the last chapter, we talked about triple being the strongest, then double, then single. And so check out that order. So this right here is an ultra important slide. I would definitely keep referring back to this slide, because this slide is basically going to summarize what the entire chapter is going to talk about in terms of water being special and awesome for life. And all of these factors have to do with the cohesiveness and the all of these factors have to do with the water molecule being polar. So to get started, the first one is the cohesiveness and adhesive behavior of water. What cohesion is the ability for the water molecules to hold together. So when the water molecules hold together, that is called cohesion. And so it is the cohesion that basically helps transport water against gravity and up to the tip top plant. Adhesion is when the water molecules are going to be attracted to other substances and molecules. And so basically the water molecules will adhere to surfaces. And so that's the difference. But the reason why is because of those hydrogen bonds. And those hydrogen bonds are made possible because of water being polar. So as you can see here, this is how your water gets from the very bottom of the roots all the way to the tip tops of the trees. Okay, so looking here, I'm going to go ahead and draw myself a nice big leaf so you can see what's happening. Here's a nice big leaf. Okay, we're going to pretend like that leaf is extending off of that tree. Hopefully you like my leaf. There you go. So you could go to the blue for water molecule. I'm not going to draw the H, the 2, and the O. It makes it, well, I'll draw a couple of them. Makes it kind of hard. There's an O, and there's an H, and there's an H. And this is partially negative, partially positive, partially positive. Hopefully you can see that. So what I'm drawing here is like a little sign and positive. Okay, so that's what that little fish sign, they do it a little bit differently too, but this is like the lazy way to do it. Okay, so because of cohesion, this water molecule is going to be attracted to the one next to it. Boom, 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 just like such. And then the next, and then the next. Okay, I know it's getting real sloppy and real ugly, but go ahead and refer to right here. And that's what I'm trying to show you. And so what happens, I'm just going to go ahead and draw water like this on the surface of the leaf. Whenever you have sun, there's the sun. I'll draw a little happy face for him. There you go. There's his nose. So the sun is going to help with evaporation, and then you're going to have wind. I'll do wind in black. Then the wind is going to blow, the wind is going to blow, and then wind blows. And so what happens, the water is going to come from the inside of the leaf to the outside of the leaf. And that process is called transpiration. Just like we perspire, your plants are going to transpire. So that is called transpiration. And when that happens, the water that is on the interior of the leaf is going to come to the exterior of the leaf. And then because of the wind and the sun, that water is going to evaporate. Evaporation, just like such. So when that evaporation happens, that water molecule is going to pull on the next water molecule, which is going to pull on the next water molecule and the next and the next and so forth. And then as you can see here, you get the pulling of the water molecules from one to the next. And so that is what is going to help to pull the water molecules from the tip top of the tree. I'm sorry, to the tip top of the tree from the root system all the way down. And so that is adhesion. So the cohesion is that phenomenon where the water is actually sticking to the walls of the internal tubes of the plant. And so, yeah, so that's what makes life possible. If it weren't for this, the height of trees would not even be possible. We would still be stuck with moss. You'll learn that when you take 112. All righty. Go ahead and take a screenshot if you love it. I'll give you a second. All righty, so let's go next. So surface tension is going to be a special application of cohesion. It's going to be measure of how hard it is to break that surface of the liquid. So basically it's cohesion, but on the surface of the water where the air and the water meet, your hydrogen bonding is going to be greater and stronger on that surface. And so that is what makes water striders and insects able to basically just rest on the surface of the water. It looks like they're resting on a thin layer of plastic or glass or something. But it all has to do with a thicker, I should say a stronger hydrogen bonding on the surface of the liquid. So the second property of water. The second property of water is going to be the moderation of temperature by water. So water is special in that it is the only substance that is going to behave in this manner that can absorb lots of heat, but still withstand large changes in its own temperature. So when we talk about heat, heat is a measurement of energy, okay? And the temperature is that how we basically are able to relate the amount of heat, the great amount of energy. And so what I'm trying to tell you is water can absorb lots and lots and lots of energy and maintain its own temperature very well. And so what water will do, water will absorb heat from warm air and release heat to cooler air. So let's draw, I'm going to pretend that it's a cold, cold day today, right? So let's say I don't put my dogs outside. They're spoiled. They go outside to potty, maybe jump around, and then they're coming right back in. But a long time ago, I had a dog that like stayed outside. She had access to the garage. She would just go back and forth and do her thing all day. While I was at school, she would just go hang out in the garage and it was warm in there. And I don't know, just old school dogs, I guess. But let's say I put out a hot bucket of water because I wanted to make sure that her water wasn't going to freeze. Okay, hot water. So I put in hot water out here for Shabu. Her name was Shabu to drink. Okay. So it's really, really cold. I don't know if I can make a snowflake. Oh, well, all snowflakes are different anyway. So I think that snowflake pattern looks pretty. We're going to say that that is a snowflake and it is cold out here. Okay, so your heat is going to travel from an area of hot to cold. Okay, so the cold air does not cool down the hot water, but what happens, the heat from the hot water is going to leave the hot water and it is going to transfer to the cold air because in your law of thermodynamics, your heat is going to travel from an area of hot to an area of from an area of greater heat to an area of lower heat. So let's go ahead and do the opposite. Let's pretend it is a really hot day and I put my dog's water outside and I threw like cold water. I even threw some ice cubes in there because I wanted to make sure that water was cold. And throughout the day, the sunshine. Oh my gosh, it is just blaring hot air. So what's going to happen is the air that is from the outside, no, not the air, excuse me, the heat from the outside is going to transfer to the colder water. And that is going to basically warm up that colder water. So just remember, heat always goes from hot to a colder area. So if you were to be out on a football game and you're sitting out there at the football game and you start to shiver and you're like, oh my gosh, and you're on the benches, right? And you're like, oh, I'm getting cold. No, you're not getting cold. What you're doing is you're releasing your heat. That's what's happening. You are releasing your heat. So that's why when you get up to go to the bathroom, you actually released your heat to your seat. And then your friend scoots over and decides to sit in your seat because your seat is warm, because you released your body heat to your seat. Now they're going to take it. All righty. So water can absorb or release large amounts of heat with only a slight change in its own temperature. So let's talk about energy. Last chapter, we talked a little bit about energy, and we talked about potential energy, and we dipped into some kinetic energy. This chapter, we're going to talk more about kinetic energy. And kinetic energy is going to be energy of motion. The kinetic energy that is associated with random motion of atoms or molecules is going to be called thermal energy. And the temperature is a way to measure that energy. That's how we make sense of the energy, by checking the temperature. And so your thermal energy can be transferred from one body of matter to another. And that is what it right there is defined as heat. So when you are at that football game and you sat in your friend's seat when they got up, you are feeling the transfer of their thermal energy to the bench, which is now left behind on the bench. And now that thermal energy is being transferred to you in the matter of heat. So when we look at a calorie is going to be the amount of heat required to raise a temperature of water by 1 gram, temperature of 1 gram of water by 1 degree Celsius. So it's a 1 to 1 to 1. 1 calorie takes to raise 1 gram of water by 1 degree Celsius. And I'm actually going to pull out a chart for you here in a moment. Let me go ahead and stop share. I am now. Okay, so let's go ahead and look at this chart. This chart is a great chart to illustrate how it takes 1 calorie of energy per 1 gram of water to increase the temperature by 1 degree Celsius. Okay, so just looking at this chart, just number one, let's go ahead and just get some perspective. I'm going to go ahead and get some perspective. In our lab, we have this little tiny beaker. It's the smallest beaker that we have. It's a 50 milliliter beaker. Okay. And then it's a 50 milliliter beaker, meaning that we can hold 50 milliliters of water in that beaker. And if I were to figure out how many grams of water in that beaker, I can tell you it would approximately filled right about here. It's a very, very smallest beaker. I can hold it in the palm of my hand. Okay. So if that gives you any, any perspective, so I'm going to put 50 grams, and then the total beaker can hold 50 mils. So the grams, we actually weigh it out to see what the mass is. The milliliters is the volume, if you recall. Actually, yeah, we did that already. So, all right, anyway, so just give you some perspective on what a gram of water is. It's tiny. It's very, very tiny, just a little bit. So now that we got that perspective, let's go ahead and look at our chart. You can see here, this is temperature in degrees Celsius, okay? And this is how many calories. Calories is going to be the measurement of heat. because we need to put value to it per gram of water. So calories of heat energy per gram of water. So I'm going to start here at 60 just because everything else is in my way. To go from 60 to 61 degrees Celsius, you input 1 calorie of energy per 1 gram of water. To go 61 to 62, another calorie of energy per 1 gram of water. I know my jumps look big because it's really hard to do minute, okay? Just imagine I am going from 60 to 61 to 62, 63, 64, 65. Every time I increase the amount, the temperature of the liquid, I have to input 1 calorie of energy per 1 gram of liquid. So if you can imagine having actually 50 grams of liquid, that's a lot, okay? So that's going to take a lot. All righty, so once we get to this certain point here, and we want to turn that liquid into gas, then we have to input 540 calories of energy to transform 1 gram of water from a liquid state into a gaseous state. So essentially what's happening is, I'm going to go ahead and draw off on the side. I'll draw it in yellow. If you recall water, your water looks like this: oxygen, hydrogen, hydrogen, right? And then you have oxygen, hydrogen, hydrogen, and you have hydrogen bonds. And then oxygen, hydrogen, hydrogen. You got hydrogen bonds, hydrogen bonds. So just review what your water looks like. So this is liquid water. So every time you put more energy into the liquid water, it is going to start straining the hydrogen bonds. So when you add more energy, it adds more strain. When you add more energy, it adds more strain to those hydrogen bonds until you get to this point around boiling point that your liquid water is ready to turn into gaseous water. And when that liquid water is ready to turn into gaseous water, what's going to happen? These hydrogen bonds are going to break. Hydrogen bonds are going to break. No longer straining. Excuse me. And now that is hydrogen gas. That is water vapor. Excuse me. So with this, just imagine watching water boil. Okay, you put your pot on, you see your liquid water, you put in your heat, and you add more and more and more. I'm glad I got a mute button, man. Okay, so with that, pretty soon you see your water, as you add more energy in it, you see your water start to kind of turn over. Then you start to see it bubble just a little bit. Then it starts popping even more. Then eventually it goes into a rolling bubble. And then you start to see steam come out. So what's happening when you put that energy in, initially those bonds are straining. And then when the water starts to boil and that vapor starts to come out, those hydrogen bonds are breaking, and the liquid water is going to become gaseous water. If you leave that pot on long enough, eventually you will boil out all of that liquid water and it will all be gas. All righty. So with that, I know this is such a fun lecture, guys. This is not even something I'm going to be able to keep for future classes. This is something I'm just trying to get through. Sorry. So you have to put energy. I can't spell energy. Let's try that again. This is clear all. Heat, energy in to break bonds, to break those hydrogen bonds. I'm telling you test question answers here, okay? To go from liquid to gas, you put heat energy in to break hydrogen bonds. All righty. Now, let's go the other way. I'll use blue instead. Hopefully blue shows up on the back. Whenever you want to change gas into liquid, condensation happens. And so to get gas to change to liquid, you need to remove, well, that shows up pretty good. You need to remove energy, specifically heat energy. When you remove that heat energy, that will form bonds. That's how you get gas turning into liquid through condensation. All righty, that right there is test questions, okay? Heat energy in breaks hydrogen bonds, changes liquid into gas. Remove heat energy from gas, and that is going to form bonds, hydrogen bonds, and that is going to change gas to liquid. Forms hydrogen bonds. All right, friends, let's go the other way around. Take a screenshot. I'm going to take a moment. Okay, so let's go ahead and clear that. So the next, if you want to cool, to go from one to the next. As you go from 1 degree down to the next, you remove a calorie of energy per gram and so forth. Take out 1 calorie of energy per gram to go down 1 degree, 1 degree, 1 degree, until you get to this point where liquid water is going to start freezing into solid water. And in order to do that, the removal of 80 calories of heat energy needs to be removed, MOVED, to change liquid into gas. I'm sorry, change liquid into solid. I'm doing the best I can here, guys. So that is basically when your water is going to freeze. And we're going to talk about that next phenomenon, here next. So go ahead and take a screenshot. And by the way, that's 80 calories of energy per gram of water in order to freeze liquid water into ice. Okay, let's go ahead and stop share. And all righty. So back to the calories. Whenever we look on packages and we see calories on packages, essentially what we're looking at kilocalories, which means thousands of calories. So 1 kilocalorie equals 1,000 calories. So if you look at a package of food, I was looking around to see if I had anything. I actually do have something here. I have a granola bar, and the granola bar says it is 190 calories for 2 bars. So times 190 times 1,000. So 190,000 calories. So nobody would ever eat if they saw that. So anyway, so food calories are much different than scientific calories. All right, so specific heat. We're still on the same subject and the ability for water to moderate temperature. And so that really is in regards to what is called the specific heat. So the specific heat of a substance is the amount of heat that must be absorbed or lost to raise 1 gram of that substance by its temperature by 1 degree Celsius. The specific heat of water is 1 calorie per gram per degree Celsius. So that chart that I showed you was illustrating the specific heat. That just gives you a name for it. Like I told you on the chart, this is just kind of repeat. Heat is being absorbed when hydrogen bonds break, and then heat is being released when hydrogen bonds form. And we're talking about heat is being absorbed by the atmosphere when hydrogen bonds break from the water. So just don't let that kind of, just remember, think about boiling water. When you go from liquid to boil, you break bonds. And in order to do that, the water had to absorb heat. So just if you think about that, then you can go backwards from there if you need to. So this right here is to illustrate how water is such a great, wonderful moderator of temperature. So I think I'm going to need to do black line. So if you look at Los Angeles is right here. And if you slide straight in from Los Angeles, you can see it's right about the same latitude as Riverside, California. But because Los Angeles, California is near the ocean is so huge that you can see it's 68 degrees Celsius in the ocean. And that helps to moderate the temperature of Los Angeles versus Riverside. Oh my gosh, Riverside has a huge, huge temperature increase. Even though they're the same latitude, it's because there's not a large body of water near Riverside to absorb all of that solar energy. And so these average temperatures are 21 degrees higher. So pretty crazy. All righty. So the high specific heat of water also helps organisms to maintain their internal environment as far as they're controlling their own internal heat environment. So evaporative cooling is made possible because of water's specific heat. And even specifically, it's got a high heat of vaporization. Just like I showed you on that chart, 540 calories it takes to change 1 gram of liquid water into gaseous water. And so evaporation is basically going to transform liquid to gas. And that helps with evaporative cooling. And so as that water, basically as you sweat through your pores, and the water comes from the internal portion of your body to the external portion of your body, that water is then going to evaporate off your body. And when it evaporates off your body, it is going to draw heat out of the body and off the body with it. And that helps to stabilize organisms' body temperatures. All righty. The third property of water. Third water property is the fact that water expands upon freezing. And so because frozen water is expanded, meaning less dense than liquid water, that is what is going to make ice float. So when you see your test questions, I want you to make sure that you are reading the test question, okay? Because just because you see that the hydrogen bonds are going to be more ordered doesn't mean that that's necessarily the right answer. you need to make sure that you are seeing that ice is less dense than liquid water. Okay, just giving you a heads up on that. So your water is going to reach its greatest density at 4 degrees Celsius. And as it goes from 4 degrees to 3 degrees to 2 degrees to 1 degree to 0 to and changing into ice, it is going to actually become less and less dense. So as water cools, and so as water cools, say from 10 degrees Celsius to 4 degrees Celsius, it's going to, its density is going to increase, right? But then at 4 degrees Celsius, heading down this way, 0, i.e. ice, then density decreases. So, all righty. Let's go ahead and show a picture of that. Go ahead and take a screenshot if you can read that. It says density decreases. As you can see, I too could have been a doctor with my handwriting. So let's go ahead and illustrate this. All right, so we're looking at liquid water. And so as we look at liquid water here, we can see that I actually want to do it, let's clear that, do it in yellow. Yellow didn't take. So you look at liquid water here, you can see hydrogen bonds breaking and reforming, okay? The hydrogen bonds are not set. This is not always bonded here, and that's not always bonded here. What they'll do is they will dance around and continue to break and reform and break and reform, okay? Excuse me. But then when your water freezes and turns to ice, the hydrogen bonds stabilize and they will stay fixed in this expanded state. So this expanded state is going to form a lattice with all of those water molecules, okay? So because of this stableness and they are expanded, ice is less dense than water. When I'm saying less dense, I want you to think about this. In this area of volume, you're going to have less actual H2O molecules per area of volume, and compared to an area of volume of liquid water. If you have a comparable area, but this area will actually have more actual H2O molecules within a comparable area. So the density of the molecules in this area of water, there's more molecules. So it's more dense being liquid versus less dense being ice. And it is for that reason that ice floats. And because ice floats, that makes life possible. Because if ice didn't float, you wouldn't have organisms being able to live underneath the water. And so what would happen, you would be like Scrat. Let's see if I can draw Scrat. Draw. You guys remember Scrat from Ice Age, right? I'm gonna draw his little legs and little hands, right? There's Scrat's little legs and hands. There you go. He needs some, on Scrat, he had some tusks on Ice Age, if I remember. There you go. Beautiful little Scrat. But if you remember, every single episode when they started, or at least the first one, Scrat was frozen. He was frozen. And then he started wiggling when an ice age started melting, he started wiggling his little nose, and then he started wiggling his head, and then he reanimated himself. Okay, so friends, that doesn't really happen. Now, don't get me wrong, there are some bacteria that are reanimating right now in the frozen tundra of Russia. That's possible, but bacteria are special. So you don't actually have organisms that can freeze and reanimate. So obviously ice age is wrong. So it's a really good thing that your water will go ahead and freeze on your ice will freeze on top of your water. And that way these organisms that are underneath the water, they can live. And that will actually help to insulate the water too and protect them from the elements on the other side of the ice. And so that was a pretty darn good scrap, I think. My first one. All righty. So we're not going to talk about global warming yet. We'll talk about global warming in another discussion whenever we go into after our photosynthesis. Okay, so your fourth property of water. Your fourth property of water is water's ability to be a solvent for life. Okay, this is huge. Water has the ability to dissolve many, many different other polar molecules and also ionic molecules. And so because of that, that is literally what makes it possible for organisms to live, water's ability to be an awesome solvent. And so let's go on some definitions. A solution versus solvent versus solute versus aqueous solution. All right, I'm going to read the definitions first. Then I'm going to go ahead and pull up a little slide and show you, and actually show you. So what a solution is. It is a liquid that is complete homogeneous mixture of substances. Okay. You might want to screenshot this if you don't have this written on the side. A solvent is going to be the dissolving agent of the solution. A solute is going to be the substance that is dissolved. And in an aqueous solution, water is always the solvent. So now that we got those definitions out of the way, let's go draw a picture. Okay. So let's go ahead and draw myself a beaker here. Okay. And then here is the liquid in the beaker. Actually, let's go ahead and make that liquid blue because I'm going to make that water. Make that liquid in the beaker. Okay. So I'm going to have a bunch of tiny little dissolved particles in the water. And let's see if we can make them cute. Make ovals. There we go. All these tiny little dissolved particles. Sorry about the naughty dogs. What happens is other people walk their dogs and my dogs are jealous because they just go on car rides. All righty. So all of these tiny little dissolved particles are called solutes. All right. So I always think about solutes like this. Solutes are the smallest out of everything. So the solutes are the tiny little dissolved particles. So I always remember that solutes are cute because they're so cute and tiny in them to being dissolved. All righty. So then next, let's go ahead and go to the solvent. The solvent, oops, I'm still on that. The solvent is all of the liquid that dissolves the solute. The solvent is the dissolving liquid. Boom. dissolving liquid. All righty. So you got solutes, you got solvent, and then you have yourself put the solute and the solvent together. And that is what defines this as a solution. So think about the solution to the whole problem, the solutes plus the solvent. And because this solvent is water, because most solvents are going to be water in a biological medium, we're going to call this an aqueous solution. All right, feel free to take yourself a screenshot. Okay, let's go ahead and go back to your PowerPoint. All right, so your water is very versatile, and that is all because of water's polarity. So when an ionic compound is dissolved in water, each of those ions is going to be surrounded by a sphere of water. And that sphere of water is going to be called a hydration shell. I would definitely put a little star on the next slide because we are going to see that probably on a test, the hydration shell. So as you can see here, you have your salt. So sodium chloride is what we're looking at here. You drop some sodium chloride in your water. Okay, what happened is because sodium chloride is ionically bonded, the sodium and the chlorine are going to separate and they're going to be surrounded by the water. And so because your chlorine is a negative anion, the positive ends of the water are going to surround, they're partially positive, are going to surround the chlorine in its hydration shell. Okay, so your sodium is a cation having a positive charge. So the partially negative ends of the water molecule are going to surround the sodium. And that happens for every single one of those salt molecules for the sodium chloride atoms. And so that is literally what makes salt dissolve in water. Okay. At some point, you can actually oversaturate water where there's not enough water molecules to surround the salt. And that's when you'll end up with the salt basically building up in the bottom of the solution if left alone. And so there's only so many hydration shells that can take place. You have to have enough water to surround and dissolve all of the salt. You've experienced this before. So not only can you do this with your ionic molecules or ionic compounds, can also do it with larger polar molecules like proteins. So here's your protein right here. The big purple thing is a protein, the whole thing. And you can see the water molecules are surrounding the protein molecules. So protein molecules are polar molecules. And the reason why is throughout the protein molecules, there's an unequal distribution of electrons. And that unequal distribution of electrons causes electronegativity and electropositivity in specific spots. And it is that unequal distribution of electrons causing that, making that polar. And so as you can see here, your partially positive end on the hydrogen end of the water is going to be attracted to that partially negative portion of the protein. And then the partially negative end of the water, the oxygen end, is attracted to that partially positive end area on the protein. And this is what helps to dissolve protein. So if you've ever had a protein shake, you know you need a lot of water in order to really get that protein shake dissolved. Okay. So you've done this before with sugar. Sugar is also a polar molecule. And if you've ever made Kool-Aid and then you put Kool-Aid into the water and then you put sugar into the water and you mix and mix and mix and you look at it, you're like, oh, that's not enough sugar. And then you put some more. That's not enough sugar. And you put some more. And then pretty soon your sugar won't mix with your Kool-Aid anymore. And you got clumps of kind of little bits of sugar in the bottom of the Kool-Aid. And you're like, yeah, all right, that's enough sugar. So that's an example of oversaturating a solution. All righty. Hopefully you've been there before. As a kid, that's the best. As an adult, that's called diabetes. All righty. So hydrophilic and hydrophobic soap substances. So basically, up to this point, I have been describing hydrophilic substances. Hydrophilic substances are substances that have an affinity for water. They are water loving, okay, in quotes. Hydrophobic is exactly how it sounds. They are afraid of water. They do not have an affinity for water. And so oil molecules are going to be hydrophobic. And the reason why is because for the most part, they have non-polar bonds. And because overall, like relatively, they are non-polar, they don't have any electronegativity to attract the water and for the water to dissolve it, like we just saw on the last slide. Instead, the water is not going to dissolve it. And that's why they say that oil and water do not mix. And so most of your chemical reactions in organisms are going to involve solutes dissolved in water. And so when carrying out experiments, and this is where we start getting into I hate this. We are going to use the mass to calculate the number of solutes molecules in an aqueous solution. Okay, so we're starting to get into molarity. Now, before I go into all of this, I want to make sure that you guys have taken a screenshot of this right here. Take a screenshot because I want you, we're going to actually talk about this. I want to make sure that you definitely have this because when we're talking about molarity, we're going to be talking about the solvent. We're going to be talking about the solutes and the mass of those solutes and the solvent in milliliters. So let's go ahead and write that down right now. So when we do the solvent, it's going to be, the solution. Wait, solutes. I need to take a, that's what I thought. So molarity, molality, two different things. So we're going to be talking about the solution in milliliters. Excuse me. The solution in milliliters and the solutes. The solutes, we're actually going to be talking about the solutes in what is called moles. Okay, well, because we don't really connect with moles in the same way. And when we measure out the small molecules called the solvents, and we'll put those small molecules and measure their mass out, we will actually see a connection in grams. Okay, but grams and moles are not the same. But in this next slide, I'm going to show you the connection. So make sure you have that. We're going to go back to your PowerPoint. So when you're in lab, okay, I want to basically give you value to what it is I'm about to say. When you're in lab, I'm going to put a bunch of solutions out. And on those solutions, you're going to see labels on the bottle. Okay, like for example, you might have a bottle here that has a label and it says a 0.1 molar solution of sodium chloride. Okay, that's not very much actually. But when I'm talking about that, I'm talking about how much concentration of sodium chloride is in the solution in comparison to the liquid in the solution. Okay, so that's what we need to understand and know molarity for. So molarity is going to be the number of moles per solute, the number of moles of solute per liter of solution. So this right here is something that you should absolutely have written on your paper on the side at all times whenever you're doing any molarity problems. So that way you can understand, that way you can identify what you're looking for, okay? So the overall molarity, when I'm talking about the molar solution, that's what we write down on the bottle, the molarity. But what that means is it's talking about the number of moles of the solute, all the tiny little dissolved particles, in conjunction with the liters of the total solution. Okay, so these are calculations you're going to have to do. Luckily, I got some videos on to watch for you guys to watch. So I'm going to refer you to my already pre-made videos where you can see me going through many molarity problems. So this is just a little step-by-step thing. First thing you would do in calculating molarity is you need to calculate the molecular mass. And the molecular mass is essentially the moles of, it's going to tell you how many moles of a solute. And so the molecular mass is going to be equivalent to the sum of all the masses, sum of all the masses of the atoms. And once you get the sum of all the masses of the atoms, we give it a unit label, and that unit label is called grams per mole. Okay. So you're like, what is a mole? Well, a mole is going to be equivalent to the number of molecules in that solute. So Avogadro's number is 6.02 times 10 to the 23rd, and that is equivalent to 1 mole. Luckily, because I teach what I teach, I don't really have to talk in Avogadro's number because I'm not a chemistry teacher. Instead, I get to talk in something I can understand, in that 1 mole is equivalent to 1 gram. Okay, so really, this is what you are going to be measuring is 1 gram, and then you're going to equate that to how many moles so you can do the calculation. I know I have thoroughly confused you, but no worries. We have some ways to get on out of that. So the next step is to calculate the liters of solution. So I'm going to actually play a video for you. For those of you watching this at home, I'm just going to refer you to the video, and that is the video from lab number 5, and it is going to be how to calculate molarity. Practice it. Okay, at this point, you have watched your molarity videos that are found in your lab number 5. There's the one that's Mr. Kazi molarity videos, and then there's also my example molarity videos too. If you are finding that you are needing more examples, I have definitely many more videos, and we can do some practice stuff when we do the lab. So, excuse me. Alrighty, so with this, water is so important. Biologists are always seeking life on planets that have water, okay? Because we can't live without water. To date, more than 200 planets have been found outside of our solar system, and there's evidence that a few of them actually have water vapor. In our solar system, Mars has been found to have water. And so you can see here, there's some actually ice in the ground in Mars. And then you can also see remnants of water flow in the actual geographical structure of Mars itself. So with this, we're still talking about water being an awesome solvent. Okay, so when we discuss water being an awesome solvent, we have to include the fact that water can become an acidic solution or a basic solution also. I shouldn't say water can become, water can disassociate an H and cause other solutions to become acidic or basic. Okay, there we go. So your water is H2O, if you recall. Okay, so whenever you have H's that are disassociated and broken off, these are called hydrogen ions. Okay, and then what's left is the OH. And because the H plus left, that means makes the OH minus. And this is called a hydronium ion. So this H plus can actually go join another water molecule, making what is called a hydronium ion. And you're like, what? All right, no worries. Let's go ahead and just show you this. Your water is in a constant state of fluctuation. So as you can, the covalent bonds actually do make and break in water. And so they're still strong. Don't get me wrong. They're still stronger than hydrogen bonds, but they will break. And so as you can see here, the, get my pen to work. The hydrogen from this water molecule attached to this water molecule, that made this one a hydronium ion, and that is a proton. It's a positive charge. And this made this one a hydroxide, and the hydroxide has a negative charge. Because of this situation right here, that is what is going to lead to solutions having a change in pH, okay? And the fact that there's a situation where the hydrogen is free floating before it switches, right? This free floating hydrogen leads to acidic solutions. Alrighty, so let's get to it. Then that constant change, you're going to have constant concentrations of hydrogen H pluses and OH minuses situation. And that can change the chemistry of the cell. When the hydrogens and the hydroxides are equal, it's pure water. But when they are not equal, that leads to either acidic or basic solutions. And so what is an acid? An acid is any substance that has an increase in hydrogen concentrations, and a base is a substance that has a reduction in hydrogen concentrations, meaning it's got a lot more hydroxides. So there are strong acids and strong bases, and the strong acids and strong bases are when the ionic compounds dissociate completely. So hydrochloric acid, HCl. HCl will dissociate to become H plus and Cl minus. This is an extremely strong acid. And the reason why it's extremely strong is because the reaction goes in this direction and usually does not go back. Okay, they usually dissociate completely and don't return back. An example of a strong base would be sodium hydroxide. Sodium hydroxide is going to dissociate into the sodium plus and the OH minus. And once again, it is a strong base because the direction of the reaction goes in this direction and it doesn't go back. Okay, versus weak acids and bases. Weak acids and bases are reversible. They go back and forth and back and forth. Carbonic acid, H2CO3, H2CO3 is going to dissociate an H, boom, and become HCO. Well, that's not a minus right there. And become HCO3 minus. And so when it does that, it causes a solution to become acidic because there's free floating hydrogen protons. Okay, but this is considered, carbonic acid is considered a weak acid because it can return back to its form. So the chemical equation can dissociate the H and then it can also go back and become carbonic acid again. So that's important to know, and we'll talk about that here in a little bit. If you want to take a screenshot, now's a good time to take a screenshot. Okay, so what is an acidic solution? Acidic solutions are solutions that have a pH of less than 7, and a basic solution or basic or alkaline has one that's greater than 7. 7 is neutral. Okay, so most of your biological fluids are going to be in the range between 6 and 8. It really depends. The stomach is way low, very acidic. And then you have your intestines, that certain parts of the intestines are going to be more basic. Your blood is going to be 7.4, which is going to be more neutral. So it depends on the organ and the fluid. So as you look at this is a pH scale. So in your pH scale, you are going to see from the smallest value of the pH scale, the lowest number being 0, to the highest number being 14. The middle number is 7. 7 is considered pure water. It is considered neutral, okay? The reason why it's pure water is because the number of hydrogens in a solution are going to be equal to the number of hydroxides in a solution. Look at the solution to the left, count them out. Let's count the hydrogens. 1, 2, 3, 4, 5. 5 hydrogens. Count the hydroxides. 1, 2, 3, 4, 5. So you get them all together and they make water. All those hydrogens and hydroxides make perfect water. So as you go higher in the number of the scale, okay, I'm not looking up, I'm looking in the higher number, headed towards the larger numbers, you become more basic or more alkaline. And as you can see, more basic solutions are going to have a greater number of hydroxides in the solution. We can count here the number of hydrogens and hydroxides. You have 1 hydrogen to that hydroxide makes water. 1 hydrogen to that hydroxide makes water. Well, now you're just left with a bunch of hydroxides, and those extra hydroxides are going to make that solution basic. Okay, hydroxides, lots of hydroxides can cause cellular damage, just like an acidic solution can too. So let's look on the lower of the scale number. The lower the scale number is going to be your acidic solutions, and your acidic solutions have more hydrogens in comparison to hydroxide. So let's go make some water. Let's see, this hydroxide goes with this hydrogen, makes water. This hydroxide goes with this hydrogen, makes water. Now all you have is excess hydrogens. So this up here is an acidic solution. Okay, so acidic solutions are very damaging, cellular damage. So as you look at this pH scale, it looks like 14 points, but it's not. It actually goes in increments of 10, a logarithmic scale of 10. So what that means is, as you go from 7 to 6, as you go from pure water to urine, you are becoming 10 times more acidic. So urine is 10 times more acidic than pure water. Look at black coffee. Black coffee has a pH of 5. So black coffee is 10 times more acidic than urine. So let's see, black coffee versus water, 10 times 10. So black coffee is 100 times more acidic than pure water. Look at tomato juice and beer. There's another 10 times. So if you have yourself an ulcer and you don't drink very much water, and you find yourself drinking all kinds of black coffee, and you have some tomato beer, and you have cola throughout the day, lots of wine, you throw some vinegar on your salad with some lemon juice, and then you wonder why your gastric juices are just extremely acid. So what do? You end up going to the other end and you grab yourself some milk of magnesia, and your milk of magnesia is actually a weak base, and that milk of magnesia will help to bring your stomach acid back to a 2, because all of these other ones are helping push that stomach acid even further into the acidic range, even more than it needs to be. So let's go the other way on the scale. As you can see, as you head down the scale, when you head down the scale from pure water to seawater, boom, it is going to be 10 times more basic. Okay, so I don't know if you've ever been out to sea, but drinking seawater is not good. Oh my God, it is terrible. So what else do we got more on the basic? Milk of magnesia, ammonia, bleach, oven cleaner. The inside of your small intestines is basic. And so just know it's on a logarithmic of 10. So it's really important. You got to know your logarithmic scale. I know we only have 3 minutes left. We actually are about done. Let me go ahead and talk about some buffers real quick. Your buffers are going to be substances that will help to maintain the pH of a solution within the range of the buffer. Meaning, if I had a solution here that was a buffer, and different buffers have a different number. Basically, your buffers are going to be weak. They're going to be weak acids and weak bases. So let's say I had a solution here that was a buffer of 4, and its pH was 4. And then I dropped in, drop, sodium hydroxide, which is a base. It is the strongest base, okay? I dropped it in, little drops, little drops, little drops. This buffer is going to maintain the pH of 4. It's going to maintain it the best it can for a really, really long time. Versus if I were to take this sodium hydroxide and drop it in water, water is a 7, and I drop it in water, oh my gosh, that pH of the water is going to, it's literally within a couple of drops, it's going to shoot to a pH of 11 or 12. So the buffer can maintain the pH versus something that is not a buffer doesn't. So just know buffers are not always number 7. A buffer is a weak acid or a weak base that will maintain its own pH, even when adding in a base or an acid to it.